just some tools that I want to teach you to begin with, and then I would set you up for work energy principles after having communicated a few general tools. Now, first of all, say this is any curve, all right, and say this is the origin. AB is the curve. Now, if there is a point P with position vector r on this curve, it means if O is the origin, what it means is that OP is the vector r. OP is the vector r, position vector of the point P as seen by O. That's what it means, isn't it? If P has coordinates x comma y, then the position vector of P is going to be given by, say if this is the xy plane, it's going to be xi cap plus y j cap, right? All of you understand this? Yes or no? Say at a certain instant of time, the particle is at the point P, whose position vector as seen by O is r. R is xi cap plus y j cap. Now, after a while, let's say the particle moves to the point Q. This vector is r. And the position vector of Q is, say, r plus delta r, which means the vector OQ is r plus delta r, position vector of the final point, right? Now, the vector PQ from triangle law, realize that this is r plus this vector is the vector OQ, isn't it? R plus PQ is OQ. Right? Which means PQ, which is the displacement from P to Q, is delta R, which is change in R. Final R minus initial R. Final R is R plus delta R minus initial R, which is R, which is change in position, which is displacement, Delta means change. Right? Now, essentially, the vector delta R, that is change in R, takes you from a point P to another point Q on the curve, to a point P to another point Q on the curve. Delta R, that's what delta R does, right? Now, what we could do is, well, from the point A to some neighboring point A1, let's say the vector is delta R, that is change in R. Then from A1 to some A2, I can go from A1 to A2 with the help of another displacement, delta R. Then from A2 to A3, another displacement, another change in R, another delta R. Yes or no, right? And so on and so forth. Eventually, this delta R. That means, if I had to, in a certain sense, approximate the curve, the curve is this, right? But if I had to approximate the curve, then what I could do is, the curve could have been approximated as from A to A1. You know, essentially this curved line replaced by this straight line AA1, right? AA1, which is a delta R. A1 to A2, another delta R. A2 to A3, another delta R, and so on and so forth. So a series of delta R's a series of delta r's, which is straight lines, straight vectors, could approximate this curve, could approximate the curve. That's a approximation to the curve. Yes or no? Where delta r is a finite displacement between a point A and a point A1, a point A1 and a point A2, a point A2 and a point A3, and so on and so forth. These are finite displacements from one point to another point, right? So one could have said, all right, instead of dealing with a curve which is complicated, I could have dealt with a set of straight lines. I could have dealt with a set of straight lines, A to A1. In the process, what I compromise is, well, I'm ignoring the presence of all points between A and A1, for example. This is A on the curve, this is A1 on the curve. Essentially, this part of the curve is being replaced by this vector delta r. This is what I'm doing. In the process, it's as if I'm suggesting that, well, the particle had nothing to do with all points between A and A1. It's as if it went along this, and all that was important was as if A and A1 were the only important entities and the intermediate points were inconsequential. That's the extent to which I compromise when I replace this curve by this straight vector delta r from A to A1. So there is a compromise, but every approximation will lead to an error. Whether that error is fine to have or not fine to have will depend on the situation in which I am in, right? Sometimes it's practical to do an approximation because the loss of accuracy that results out of that approximation does not matter too much in that situation. Therefore, we say, all right, you know, this approximation, even though it led to an error, but let's say in the 4th place of decimal in my overall computations, and I can deal with it, no issues. So let's say this is what could be done. The entire curve could have been broken down into a bunch of these delta r's, one bunch of these straight lines, which are these delta r's, these vectors delta r's, right? Between any two points, see A1, A2, A3, etc., these are set of points, say some point AI, and there is a neighboring point AI plus 1 on the curve. AI and AI plus 1 are two neighboring points on the curve, right? And this is my delta r, and this is my delta r. So when I am at AI, then my delta r takes me to AI plus 1. Then my delta r takes me to AI plus 1. Now, while discretizing this curve into these nodes A, A1, A2, A3, AI, etc. up to B, like I said, there is an approximation out of practical considerations. And the number of these delta r's would be finite. I have broken down this curve into these finite set of delta r's and realize that effectively this delta r, this delta r, this delta r, this delta r, this delta r from A to B, if I have to vectorially add all these delta r's, what would I get? I'll get AB, isn't it? If I have to do the summation of all these delta r's, vector summation of all these delta r's, then from polygon law of vectors, I'll get the vector AB. Yes or no? Right? Then I'll get the vector AB. So a vectors, now these delta r's are finite, n. If I increase the number of these AIs on the curve, if I increase the number of these AIs on the curve, then the number of these delta r's will increase. The number of these delta r's will increase, isn't it? But the value of each delta r will decrease. The magnitude of each delta r will decrease, yes or no? If AI and AI plus 1 are brought closer and closer and closer, if AI and AI plus 1 are brought closer and closer and closer, what happens? Delta r tends to 0, yes or no? This is AI, this is AI plus 1, right? This is AI plus 1, right? As AI and AI plus 1 are brought closer and closer and closer, delta r tends to 0. And the number of these delta r's will tend to infinity, yes or no? right? If n are the number of these delta r's, then as delta r tends to 0, then the number of these delta r's will tend to infinity, isn't it? Right? And in the process of making these delta r's smaller and smaller and smaller, and thereby increasing the number of delta r's larger and larger and larger, ai comes closer and closer and closer to ai plus 1, right? Which means as delta r tends to 0, ai plus 1 degenerates into ai. ai plus 1 in a certain sense comes closer and closer and closer to ai. Now, as delta r tends to 0, mathematically then this delta r is designated as dr. Delta r is a finite change in r. Delta r is a finite change in r. But while delta r tends to 0, it's a very, very small change in r, infinitesimally small change in r. When delta r tends to 0, it's a finite change in r. It's called a infinitesimally small change in r. Infinitesimally small change in r. In r. And such a change in r, delta r tends to 0, such a change in r as delta r tends to 0 is designated as dr. dr. Delta is a finite change. D of r is an infinitesimally small change. Is an infinitesimally small change. You know what I'm saying? Now, while this delta r, let's say there is a point ai and there is a point ai plus 1. While this delta r takes me from a point ai to ai plus 1, skipping several points from ai to ai plus 1, skipping several points from ai to ai plus 1. Mathematically, this dr, what really happens is, as delta r tends to 0, that means delta r becomes dr. Delta r becomes dr, infinitesimally small change. This delta r, as it tends to 0, it becomes, this vector delta r, it becomes a tangent to the curve. It becomes a tangent to the curve at ai. It becomes, as this is brought closer and closer and closer and closer, this second between ai and ai plus 1, this delta r is a second between ai and ai plus 1. It assumes a state of tangency. At ai, as delta r tends to 0, this delta r directionally assumes this disposition. It assumes this disposition. This is what transpires. As delta r tends to 0, it becomes dr, and its direction becomes a tangent to the curve at ai. Its direction becomes a tangent to the curve at ai. This is what transpires. Now, while delta r skips several points between p and q, between ai and ai plus 1, this dr, which is an infinitesimally small change in r, as small as one could imagine, right? This dr is an infinitesimally small change in r, as small as one could imagine, right? And is a tangent to the curve from instant to instant. Every dr will be a tangent to the curve at the corresponding point. And where does it take you? Delta r takes me from this point to this point, right? From this point to this point. And as delta r becomes smaller and smaller and smaller, it becomes dr. Where does dr take me? Mathematically. Mathematically, this dr is supposed to take me from ai to its neighboring point. Mathematically. Physically, is there any neighboring point of any point? There is no neighboring point. But this concept of dr, this concept of dr is mathematically meant to take you from the point AI to whatever be its neighboring point. That's the whole idea in this concept of dr. This dr is supposed to take you from AI to its neighboring point on the curve. That's the mathematical notion of a neighboring point. So dr essentially is a mathematical notion of a neighboring point, and it's disposed along the tangent to the curve from point to point. This is the fact that I want you to take cognizance of. Right? Now, in principle then, while in principle then, while these delta r's are like this, which is an approximation to the curve, and there are finite number of these delta r's. These delta r's are finite from A to B, and they are all seconds to the curve, and they are approximating the curve between A and B. These drs are infinite in numbers. These drs are infinite in numbers because there are infinite number of points between A and B. So these drs have infinite status in terms of their numbers, right? And it's as if one dr, another dr, another dr, another dr, another dr, infinite. I can't draw them because I can't actually physically locate two neighboring points, so I can't really draw them. But let's say this is one dr, this is another dr, another dr. All these drs also, while delta r's are an approximation, drs are the reality. The vector sum of all these drs would be the actual curve. The vector sum of all these drs would be the actual curve. While delta r's are an approximation, drs are the reality of the curve. The vector sum of all these drs, if you add all these drs, you will still get A to B. But the displacements, drs, will take you from a point on the curve to whatever be its mathematically neighboring point. There is nothing like an actual neighboring point, but the mathematically neighboring point on the curve is where the drs will take you to. Right? And nevertheless, these drs will constitute infinite number of sides of a polygon whose closing side will still be AB. Yes or no? So if I said, what would be the vector sum of these drs? The vector sum of these drs will be the curve, will be the vector AB. That's the vector sum of these drs. It's as if, again, to just give you more physical insight into the whole thing, it's as if when I talk of these drs, when I'm talking of these drs in principle, then I'm telling you the direction of tangent at every point of a certain curve. I'm not giving you the curve. All that I'm suggesting to you is that, well, the tangent at every point of a curve is known. And once the tangent at every point of the curve is known, then the join of these such that they become tangents will give me the curve. So from the tangent to the curve is the notion of drs. The drs are the tangents, and the collection of those tangents will constitute the curve. That's the idea behind these drs. Do you get me right on this? Right? And the vector sum of all these drs, which are infinite in numbers, is the straight vector AB, because the polygon law will still apply whether delta r is finite or infinitesimally small. Right? So the concept of a neighboring point physically has no significance, but mathematically, we have given it a shape with the idea of these drs. When you are moving along a curve and you want to suggest that you have to go from A to B, then you say, all right, from A to B, I draw a tangent at A, which is dr, the vector dr. It takes me from A to B, where B is the neighboring point of A. This is how it goes. An infinite number of these drs will constitute a curve. Each of these drs will be a tangent to the curve. Clear? Now, few things which I am going to deploy. One, see, there is this basic algebra of differentials which I want you to take cognizance of. Basic algebra of differentials. One is, say for example, if I write d dx of sin x is cos x, is cos x. This is like saying d of sin x, that means small change in sin x. D of sin x means an infinitesimally small change in sin x is cos x into dx, cos x into dx. That means if x changes by a very, very small amount dx, the change in sin x would be the value of cos x, original value of cos x at that x into change in x. This is a small change in sin x. Infinitesimally small change in sin x is cos x into that infinitesimally small change in x. Now, if somebody gave you cos x dx and he said write it as d of something, he said write it as d of something, then this should be filled by what is called the integral of cos x. What is the integral of cos x? Sin x. So you will fill it up with sin x. Not only that, it could also be sin x plus constant c, because sin x plus c when integrated will give, when differentiated will give me cos x, isn't it? When I say cos x dx is d of something, then this something to be filled up with the integral of cos x. What would be the integral of cos x? Sin x plus c. Now in certain situations I want to take c as 0, I want to take c as 1, c as 2, that's my choice. It does not matter, right? Say for example, I had x squared dx and I want to write it as d of something. Then this should be filled up with the integral of this. What is the integral of x square? X cubed by 3. So this should be x cubed by 3, and plus c is optional. I could have taken as a special case c is 0 based on the situation that I am dealing with, right? The integral of x square is, so suppose I had e power 3x dx. Switch off your phone. Is d of what? D of integral of e power 3x. What's the integral of e power 3x? E power 3x by 3. E power 3x by 3. And c is optional, right? Suppose I had sec squared x dx and I want to write it as d of something, then what would this be? Integral of sec squared x, which is d of tan x. Plus c or not c, it does not matter. Suppose I had sec x tan x dx and I want to write it as d of something. What would this be? D of sec x n plus c. Suppose I had x power n dx. This would be d of x power n plus 1 by n plus 1 plus c, provided n is not equal to minus 1, right? Suppose I had 1 by x dx. I want to write it as d of something. What would this be? Log x, d of log x plus c, and so on and so forth, right? So if I had, in a very general sense, fx dx and I want to write it as d of something, then this something should be integral of fx with respect to x. Integral of fx with respect to x. That's how it should be. Clear? Now, some basic facts about these differentials. So if I had, say, y dy, what would this be? D of y square by 2 plus c, integral of y with respect to y square by 2 plus c. C mostly is taken 0, may not be. Got me? Now ddx of f1 plus minus f2, derivative of the sum or difference of two functions, like you know, is sum or difference of their derivatives, f1 plus minus ddx of f2, right? Multiplying throughout by dx, I get d of f1 plus minus f2 is df1 plus minus df2. That means d means a change. A change in f1 plus f2 is change in f1 plus change in f2. Change in f1 minus f2 is going to be change in f1 minus change in f2. This is how you want to physically interpret this, right? Say if I had d of x plus y, change in x plus y is going to be change in x plus change in y. That's how you want to understand this. D of x plus d of y. This is f1, this is f2. df1 plus df2, for example. Clear? Then ddx of a constant is 0. See, if c is a constant, that means d of c must be 0. D of c means what? Change in a constant, but there is never a change in a constant. So d of c is always going to be 0. Right? D of a constant will always be 0. Then ddx of f1 into f2, derivative of the product of two functions, derivative of first function into second plus derivative of second function into first. So this is like ddx of f1 into f2 plus f1 into ddx of f2, right? Multiplying by dx, so d of f1 f2 is going to be f2 df1 plus f1 df2, right? Yes or no? This is another rule. D of the product, that means change in the product would be change in one function into another plus change in the second function into the first function, right? That's the law of change.
So if we increase the number of multiplication like f1, f2, f3, then what will be the?
Same thing, you can apply that. You'll have, for example, f2, f3, f4 into df1 plus f1, f3, f4, df2. Same rule, na? Same rule will apply, right? Okay, then we have, so for example, you know, if you had like x dy plus y dx, for example, something like this. This is encountered very often, time and again and again. f1 df2 plus f2 df1. f1 df2 plus f2 df1 is d of f1 f2. So this is d of f1 f2, which is xy. D of xy. Right? So we encounter this very often. X dy plus y dx, that will be change in xy. D of xy. Right? Similarly, say ddx of f1 by f2, derivative of numerator into denominator minus derivative of denominator into numerator divided by denominator squared. So this is ddx of f1 into f2 minus f1 into ddx of f2 divided by denominator squared. Right? Multiplying throughout by dx, you get d of f1 by f2 is f2 df1 minus f1 df2 divided by f2 squared. This is another rule which is used time and again. Change in a ratio is change in numerator into denominator minus change in denominator into numerator by denominator squared. Right? Say for example, if I had x dy minus y dx by x squared, d of y by x, right? Very good. This is going to be d of y by x. Change in numerator into denominator minus change in denominator into numerator by denominator squared is d of numerator by denominator, d of y by x. Clear?